Welcome back. We are now discussing on this scanning tunneling microscope, different parts of the scanning tunneling microscope. In today's lecture, I will discuss on the tip sample position control, vibration isolation and electronics in the scanning tunneling microscope. What is very important in STM is to control the distance between the tip and sample very precisely in the range of angstrom. So, therefore, the spring cantilever reducers are most commonly used in the microscope, where the moments between the tip and sample is reduced by considering the two elastic elements connected in the series. As you see here, we have cantilever here, we have a STM piezoelectric scanner here, we have tip here, and this is a rigid base of the microscope, rigid base. We have here a elastic beam, a cantilever, and we have a spring here. And by choosing the right spring constant values, we can precisely control the distance between tip and sample. Particularly in these cases, at a greater k value, where this is a small k, the capital K or the spring constant or elastic constants of the cantilever should be much higher than the spring constant of the spring or elastic constant of the spring. We know from equilibrium condition, from the equilibrium condition, we know F elastic is equal to K del L, Hooke's law, which is equal to capital K, capital K del L, capital del L. So, where del L is the displacement of the spring and capital del L is the displacement of the cantilever. So, in this case, the reducing coefficient is equal to reducing coefficient R is equal to small del L by del capital L is equal to K divided by small k. So, here as you see, if we want to reduce del L, the moments of the cantilever at to which our scanner and tips are connected, in order to reduce this del L, we have to have a larger capital K value or larger spring constants of the cantilever. So, by choosing the right kind of the elastic constant or spring constant, we would able to control the position of the tip sample by precisely moving the cantilever position to which the piezoelectric scanner and tip is attached. So, this is one of the important way to control the tip sample position in scanning tunneling microscopy. Another important important point is the vibration isolation in the STM. In the STM, we want data with a accuracy of 0.1 angstrom. With an accuracy of 0.1 angstrom, if we want the data, then the vibration should be at least 10 times lower. Here vibration means vibration from outside, that means from the ground and air where the microscope is placed, and second is to remove the vibration of the microscope itself. If we want the data, if we want the accuracy of data with a scale of 0.1 angstrom, then vibration should be 10 times lower. So, vibration should be 10 times lower, means it is supposed to be in the around the level of like 10 picoampere, 10 picometer. Vibration should be less than 10 picometer scale. This is the data we need in STM. Normally, our building vibration is around, the amplitude of the building vibration is around 0.1 micrometer. Amplitude. If we want to have a vibration of this level of the system, then we need to reduce this building vibration like 100,000 times. So, it is not that easy task. So, but it has to be done to get the data of this scale. So, how it is done? First is we have to remove the we have to isolate the system from outside vibration. First we will discuss on that, how it can be done. Vibration isolation from outside, and it can be done by spring suspension. Here you can see a spring suspension is done in the right side diagram. Here omega naught is the oscillation frequency of the spring, oscillation frequency of the spring, and we have external oscillation that we can write omega ext, which is external oscillation frequency. So, now we have another factor, this is called damping factor gamma, and Q is the quality factor, and Q quality factor of the spring is nothing but omega naught divided by gamma, that is damping factor. Now, if the oscillatory frequency omega ext is less than the oscillation frequency of the spring system Wg, then the outside excitation or outside oscillation will be transmitted with a transfer function. Transfer function is written as a kappa 1 without damping. If this is less than omega 0, which is the spring, and if omega ext is equal to or close to omega naught, that means their vibration frequency are similar or same, then resonance will occur. Resonance occurs and the amplitude will increase. So, the outside excitation is amplified. That means vibration increased instead of being damped. But if, and this is the condition, if the omega ext is much greater than omega naught, then the transfer function kappa omega external will be close to omega naught omega external to the power square. So, this would be like this. Here in the left side we see the transfer function of the spring suspension system for different values of the quality factor. If we see this one like omega ext less than omega 0, then transfer function is almost 1 without damping. And here is the resonance occur when omega external is just equal to omega naught, and then when omega external is greater than omega naught, that means outside oscillation frequency is greater than the frequency oscillation frequency of the spring, then we say we are finding transfer function less. Having a transfer function less is good because less oscillation will be transmitted from the outside system to the to our system. So, we would like to have a smaller transfer function, that means smaller transfer function means oscillation will not be transmitted or will be transmitted as less as possible to the system. So, this is what the cases when oscillation frequency either equal to or less than or greater than the oscillation frequency of the spring. So, from this formula what we see that an higher external oscillation frequency or a lower spring oscillation frequency of the spring is preferred for the system. So, how we can achieve this? So, the best vibration isolation that is let us say from the building isolation can be achieved with a smaller omega naught or larger omega ext. So, this depends on the displacement length of the spring. We know as per the Hooke's law F is equal to, we know force into acceleration which is equal to k del L, we know this, and we know the equation of natural frequency of a system f 0 is equal to 1 upon 2 pi root over of k by m. So, if we place the value of m here, that is mass, we can get 2 pi root over of g by del L, this del L f 0, bringing the m value here. Now, what we see that if del L is increased, the displacement of the spring is more, then we have smaller frequency, that means smaller omega 0, that means smaller omega 0, which is prepared for us. So, for example, if we want to have, let us say if the natural frequency of the spring is 1 hertz, if it is 1 hertz, then the del L can be stretched, to 25 centimeter. If we want to have a 0.5 hertz, then del L should be like 1 meter. So, 1 meter is quite big. So, therefore, only spring suspension system is not sufficient enough to reduce the omega 0 value to a small value, omega naught, that is spring suspension system, to a small value. So, it is not enough, one point that to be noted now. This is about the outside vibration. Then if we talk about the microscope as a vibrating system, then the mechanical loop of the microscope can also be considered as a vibration system or vibrating system with the resonance frequency. Here we say system for our STM omega STM and damping constant gamma STM and quality factor Q STM is equal to omega STM by gamma STM. So, in this case, if we look at if we find the transfer function, the transfer function of the STM can be found, the transfer function of a STM is related to the external external oscillation frequency with a relation as k STM is equal to omega ext divided by omega STM to the power square. This is what they are related, and this is what the, if we look at the transfer function, and here it is a resonance occurs, that is why it is going up. So, here you see this is what in the our spring oscillation frequency, on which we have another oscillation systems. This is for STM, where the cantilever and tip are attached. So, these two have taken into consideration. Now, we will see, now we have seen here the transfer function of the STM can be small when W on omega STM is greater and omega EXT is smaller. In order to have smaller kappa STM or transfer function, we must have a omega STM oscillation frequency larger omega STM. So, then these two now has to combine. Previously, we had natural oscillation frequency relation. Now, if we consider this, we have to combine the vibrational isolation from outside vibration isolation and also STM with high resonance frequency. So, the transfer function of the combined system, that is the spring suspension and the system cases that is can be obtained as we can write the transfer function of the combined system could be is the product of both product of individual system So, K total, that is kappa total, is omega naught, that is what we got omega naught omega ext to the power square, and here we have got for system omega ext divided by omega STM to the square, which is nothing but omega naught divided by omega STM to the square. So, now we see for a smaller transfer function, we need to have a higher omega STM and smaller omega naught. So, for example, in this case, if the spring suspension system, if that is omega, if the spring suspension system, that is omega naught is hertz 1 hertz natural frequency, if the natural frequency of spring suspension system omega naught is 1 hertz, and for STM omega STM is let us say 1 kilohertz, then transfer coefficient, the overall transfer function will be, it is 1 kilohertz means overall, then K total will be 10 to the power minus 6, quite a small value. If it will be 10 kilohertz, it will be 10 to the minus 80. So, for effective vibration isolation, that means for small total transfer function, a low natural frequency of the spring suspension system, that is omega naught, this will be omega naught, is combined with a high natural frequency of the STM, that is omega STM is necessary. That is nothing but a stiff mechanical loop between the tip and sample. So, in order to reduce the vibration of the system or to isolate the system from outside vibration and also the system vibration, it is essential to have a low natural frequency of the spring suspension and a high frequency of the STM assembly. That is what we have seen here. So, STM has to be designed in a manner that both spring suspension system and the STMs with a high resonance frequency is achieved. Second point is our electronics, and that is current amplifier. After vibration, we have to have a suitable or appropriate current amplifier. As in these cases, the tip sample are very close to each other and there is a tunneling current, that is a quantum tunneling between the specimen to the tip or in opposite direction, and that tunneling current is very small in the sense that it is in the range of 10 picoampere to 10 nanoampere. So, such a small current should be measured precisely to get the accurate data. Normally noise, if there is any noise outside or if the electronics itself has a noise, then we would not able to make the measurements as precisely in the range of picoampere to nanoampere. So, a suitable current amplifier is used to amplify the current and then convert it to voltage. A typical circuit diagram of a current amplifier is shown here. As you see in this circuit diagram, there is a important part here, the feedback resistor, current in. So, the taking into complex impedance, the voltage output can be calculated using this equation. So, where voltage output is proportional to the feedback resistance, and this feedback resistance R FB is also inversely proportional to the bandwidth. R is R FB is equal to 1 upon that is pi B. So, it is normally inversely proportional to the bandwidth. So, if we increase the amplification, we will decrease the bandwidth, and this is another one point. Another point is the noise. Noise can also play an important role here. If we increase the B here, B is for bandwidth. If we increase the bandwidth, if we increase the temperature, and temperature increases because temperature also here for increasing the V output, we have to a feedback resistor value has to be high, RFP is high. When RFP become high, then there will be thermal electron generation, temperature goes high. When temperature goes high, noise also goes high. So, these are important parameters to be considered to reduce the noise and while amplifying the signal, or here the signal is our current amplify the signal. Then we have feedback controller. In STM, a suitable feedback controller is used to follow the surface topography. So, in general it controls the whole electronics. The system output, which is nothing but a tunneling current, is converted to voltage by the amplifier, and at a set point corresponds to a voltage representing a desired tunneling current. So, a particular voltage is nothing but is related to the tunneling current. So, accordingly the feedback controller determines the system input, how much the voltage to be given to get that much of current, so that we can control the tip sample distance accurately. For example, like if I have a sample here, and if I want to measure only 1 nanoampere of current between tip to sample, this is my sample a tip. So, now I want to measure only 1 nanoampere of the current. Now, if the tip comes, if tips move in the x direction, then what will happen? Then it will see a much higher current as the tip is approaching close to the sample. As it see higher current, but rather in my system I want to measure 1 nanoampere of current, tip has to move up, tip has to move up. Tip can only measure 1 nanoampere current when it is every places equal distance away from the sample, then only it will measure 1 nanoampere current. Accordingly, if I set 1 nanoampere current to be measured, my voltage to the piezoelectric scanner should be changed automatically, so that piezoelectric scanner will move the tip upward or downwards to make or to see a current of 1 nanoampere. So, this is what it does. So, the feedback controller determines the system input voltage given to the piezo element and to change the sample tip sample distance. Accordingly, the tip sample distance changes to measure a constant current, that is what we want to measure. And feedback controller is itself a very complex system, which comprises digital to analog converters and also high voltage amplifier for the piezo voltage and vertically positioning the tip position. So, it overall controls the whole electronics and it should be highly that means precise. So, what the conclusion of the today lecture? The natural frequency of a spring suspension system depends only on the extension length del L. As we have seen, this is depends on the inversely proportional to del L. Having a higher del L of the spring suspension system, we can have a low natural frequency, that is what we want. A precise for the precise sample tip sample distance, it is important to minimize the amplitude difference between the tip sample, and a low natural frequency, that is what we discussed here, of the spring suspension, and a high frequency of the STM is prepared for effective vibration isolation to a scale of 10 to the minus 6 minus 8 or minus 10 up to 10 of small transfer function value. And the current amplifiers used in STM have a large input resistance, feedback resistance, and the current amplifier converting the input current to output voltage depends on the feedback resistance, that as you have seen is directly proportional to the feedback resistance. These are the references. Thank you.